Good afternoon. Today is our great pleasure to have Dr. Cheng-Zi with us. Dr. Zhou is a physical scientist and NOAA star located in College Park, Maryland. He received his PhD from University of Oklahoma in 1995 and worked in NOAA star since 1997. He's been mainly engaged in measuring long-term changes in the atmospheric temperatures using satellite observation and evaluations of data products for climate change studies from different sources, including those from satellite retrieval, climate reanalysis, and climate model simulations. He has developed a set of atmospheric temperature climate data records capable of detecting climate trends from the lower troposphere to the upper stratosphere. He conducted satellite retrievals to derive climate products such as polar winds. He also collaborated with colleagues on using mesoscale models to simulate and analyze a variety of atmospheric clouds and coastal wave phenomena observed by satellite. He has published over 50 articles in AMS, AGU, and other leading journals, including Nature, Science, and PLOS. He has received a Department of Commerce Silver Medal Award and NOAA Administrator's Award for advancement of satellite calibration and development of atmospheric temperature climate data records. Let's welcome Dr. Zhou.
Thanks, John, for the invitation and introduction. And thank you for all for coming. And my talk is toward improved satellite measurement of climate trend in the atmospheric temperatures. This is pretty much a review of the lessons learned over the years and on the measurement of climate trend in the atmospheric temperature, and it includes many studies from other researchers as well as our own group. And then we introduce some new findings on the stability of the SMPP Advanced Technology Microsounder. Okay. The work has been done for many years in its collaboration with colleagues from NOAA, UMD, and George Mason. And I just want to thank them for the satellite processing and science support over the years. This is the outline of the presentation. First, I'm going to review the status of the satellite atmospheric temperature climate data record, CDR, including the development of the atmospheric temperature CDR and available CDRs and the temperature trend observed from these observations, and then use this observation to evaluate climate model performance and try to verify the global warming theory. And then we talk about the many issues in the atmospheric temperature CDRs, followed by new findings on the radiometric stability investment assessment in the new generation of microsounder on the SMPP satellite. And finally, I'll give a perspective on how these new findings will improve the science of climate trend measurement. Let me start with a refresh of the global warming theory. And this is the plot from the famous paper Manabi and Westward in 1967, 50 years ago. It shows the how temperature profile, we respond to a doubling of carbon dioxide in the atmosphere. This is based on simple radiative convective equilibrium model. And what it shows, if you double the carbon dioxide, the surface and tropospheric temperature, you expect the increase of about 2.3 Kelvin. And in the stratosphere, at the 2 millibar, it's about cooling about 10 Kelvin. And the ratio between them is about 4.4. The physics around here is pretty simple. The increase of the carbon dioxide, we trapped more long-wave radiation in the surface and the troposphere and causing warming there. And meanwhile, it emits more radiation to the outer space and causing cooling in the stratosphere. And because the air of the stratosphere is much thinner, so the cooling rate is much higher than the troposphere. And meanwhile, the ozone depletion also causes cooling in the stratosphere because it causes less absorption of solar radiation there. But in the long run, ozone depletion in the before 1997 and great recovery recently, so it's probably not that important in the long run. And this shows the carbon dioxide time series in the atmosphere. This is observed from NOAA site, and it shows in the last 60 years, it keeps increasing from a little bit over 300 ppm to now over 400 ppm, and it's still increasing, and it appears accelerating now. And compared to the carbon dioxide level over the 400,000 years ago, from now, it's the level of the last 50 years is the highest. So we have the global warming theory and also the increase in carbon dioxide. And so the question is, can we measure the global temperature trend, and how good are the measurement? It's not easy. At least you need 35 years of global observation so that the trend calculation can be within uncertainty of 20%. Shorter observation, you can calculate the trend, but it will not robust because of endpoint problem. Another question is, if you have the observation, is it consistent with scientific understanding? In other words, is it consistent with modeling simulation? And we have the model development significantly improved over the last several decades, and we can do some comparison over there. So we are talking about these two questions today. This is a review of the available means of a temperature trend measurement up to now. And over the surface, we have the over land, we have surface weather stations, but they're sparse over the ocean. But over the ocean, we have the buoy stations, more than 1,000 stations, and there's a big group using this data to detect the surface temperature trend. But we are today mostly focused on the atmospheric temperature trend. In the atmosphere, we have the radio sound measurement, as weather balloons. There's over 1,000 stations launched regularly every day. And but the radio sound is covered only over land, but it's sparse over ocean, so it's not considered as a global coverage. We still have maybe less than 10 stations, radar stations, that can measure. Also, the radio sound cannot reach the mid-stratosphere and the upper stratosphere. And the latest observation can reach to the upper stratosphere, but that's less than 10 stations here. And only the satellite data have global coverage, and you can measure different layers of the atmosphere, but it's a little bit shorter than the radio sound and the surface observations. But still, we have 40 years data now, and we can develop some data sets with some good confidence not good confidence. Yeah, I can say that on the trend detection. This is a satellite and the instrument that we talk about. For the atmospheric temperature measurement, we have the Microwave Sounding Unit, MSU, and the Stratospheric Sounding Unit, SSU. They start from 78 to 2007. And after that, it is replaced by the AMSU-A, Advanced Microwave Sounding, starting from 1998. And this has more channels than the other two instruments, and with better vertical coverage and horizontal, better horizontal resolution. And they start from NOAA 15 and until now, and we still have several satellites that have this instrument measure the temperature now. And going forward, from 2011, the ATMS, Advanced Technology Microsounder, was equipped on the SMPP satellite, and going future, it will be on the GPS-S series on NOAA satellite, and we're expecting it keep the atmospheric measurement until 2030 and 50 time frame. So we altogether we have a very long, nearly 7 years time series for climate trend monitoring. This is the weighting function channels of the instrument. For the MSU and the SSU, we have a total of 7 channels from the surface to the stratosphere. This is upper stratosphere is nearly 1 meter bar. This is where weighting functions, and we only talk about the 6 channels of the atmosphere. And this is AMSU and the ATMS channels. They're basically identical channels, except that one channel is not in the ATMS, is not present in the AMSU-A. They only total have 15 channels, also from the surface to the upper stratosphere. So it's a question. It's probably is to merge these channels on different satellites together, including MSU satellites, and to the AMSU-A satellite for the companion channels, and also match the SSU channels from several AMSU-A channels. The challenge is when you try to merge them together, the challenge is the calibration bias of these instruments on the order of 0.5 to 1 Kelvin. And the temperature trend in the troposphere is on the order of 0.1 to 0.2 Kelvin per decade. So a tiny error in the merging methodology or quality control, you will have the large trend differences and uncertainty. So you have to be very careful, and it took many years of effort to develop this time series. This is the issues that involved in development in the MSU, and the ATMS time series, including dynamic sampling drifting errors, intersatellite biases, viewing angle differences, channel frequency differences, instrument temperature effect, calibration drift, and so on. I'm not going to talk about detail here, but talk about some issues shortly later on. And we will now come to the exam results. So this is a merged time series from our NOAA group. This is through the MSU 3 channel. The TMT is channel 2, temperature mid-troposphere, and the temperature upper troposphere, TOT, and the temperature lower stratosphere. And each color represents a different satellite. They're well calibrated and intercalibrated and bias removed. And the issue that we talked about is that has been at least minimized. So they form a long-term time series. And And you can say in the mid-troposphere temperature is increasing at the rate about 0.1 Kelvin per decade, and upper troposphere also increasing, and the lower stratosphere is cooling at 0.3 Kelvin per decade. And you can also see some climate event such as the volcano effect, Pinatubo here, causing the temperature jump at the stratosphere. And also the El Nino, 1998, it's 2010, showing up in the tropospheric temperature time series.
Very quick, if you see from my eyes, 1998, the TMT trend itself, like a tree. Am I right, or just my eyes?
What's that again?
The TMT trend.
Yeah.
From 1998 to probably 2015, it looked like it's decreasing.
Yeah, you're right. It's from here to 1998 to here, the trend is not much. It's kind of flat. But again, if you look at the longer time series and including the last years and the last 2 years, you see a little bit increasing. So you have to have more than 35 years or longer to have a confidence on the trend. Short 20 years, it's a little bit short. I would wait. Yeah.
For TLS, you can say about the ozone recovery. But for TMT, I don't know how to explain it.
That's some other study saying that it's related to the Pacific. Pacific. I don't know, but it's just some study on that. Yeah. For the SSU temperature anomaly time series, we're dealing with a completely different set of problem that's different from the MSU and the AMSU. I'm not going to talk about the detail, but this shows the time series, the raw of the raw data before merging and the recalibration, and this is channel 1, the mid stratosphere, and this upper stratosphere, and this is top stratosphere. And so before the merging recalibration, you can see that even for the same period, and the different satellites drift to the different direction. And so after recalibration, you get them very well merged together, and all the different satellites they are very calibrated. The difference in time series basically is on the 0 line. So you can directly use them to calculate the trend, all showing the cooling trend in the stratosphere. Also, this the SSU stopped at 2007, and to continue to monitor the atmosphere trend, we merged them with the AMSU-A. One SSU channel merged with several AMSU-A channels, so that they get the equivalent SSU channel from AMSU-A. And this is the extended time series. The red curve is extended AMSU-A, and so the time series is updated every month until now. And so this is the available data set for this product. For the MSU and AMSU-A CDRs, we have the NOAA STAR, that's our group, still doing that, and the remote sensing systems at the California. They developed the same product, but sometimes we're using different satellites. And the University of Alabama at Huntsville, John Christie's group. For the SSU, AMSU, we have the NOAA group, and also at NCAR, Bill Randall merged our SSU data with microlim sounder, so have another stratospheric temperature CDRs. So now let's talk about what we learned from this temperature time series. For the mid-troposphere, this is average from the three groups, the mid-troposphere, but it's also credited from the lower stratospheric cooling effect, because the AMSU channel 2, that channel contains contribution from the lower stratosphere cooling, so you have to remove that effect. And after that, we can say the long-term trend for the last 40 years is about 0.18 Kelvin per decade. So the total warming for the last 40 years is about 0.7 Celsius degree, positive minus 0.1 degree. And this warming is not uniformly distributed over the globe. It's over the northern polar region, the warming is larger, and its warming rate is about twice or even 3 times as large as the global mean. It's not surprise. We know that from other observations, the polar region warms much larger, but this shows a global picture of the trend distribution. Yeah, this is the temperature variability over the South Pole is very large, and its uncertainty is large, and also it is a little bit cooling, but when you include time series, this is to the 2007, but if you include the time series for the this year and the last year, you see a little bit change, and it's a lot of ice cap melt over the South Polar region. That's a very interesting phenomenon over there. We need to keep more eyes on the South Polar region. That's true. Yeah. And this is the trend over the stratosphere. It's the top stratosphere, SSU channel 3. Everywhere it's cooling, and over the Canada area, it's the cooling is much larger. Over the 40 years, the temperature drop is 5 Celsius degree. It's pretty big. So if you consider individual event, you expect maybe 10 degree, 20 degree cooler than the 40 years ago. Globally, the stratosphere this is a 1 meter bar. You can the temperature drop is 3 Kelvin globally. It's also much larger than the troposphere. And now we go back to the global warming series plot slide earlier. We noticed that from this simple radiative convective model, the stratosphere cooling rate and the surface warming, the ratio is 4.4, and the observed ratio for the last 40 years is 30 divided by 0.7. We got 4.3, and the agreement is remarkably. Although we know that there's a lot of other feedbacks in the atmosphere, but I hope this is not coincident. It's really tell that observation and the simple model global warming theory have quite an agreement in that aspect. When we talk about the actual observation and comparison with model simulation, and this shows the mid-troposphere temperature time series compared with model simulation from SIMU-5 project. The thin curves, thin lines on the background are individual models. They're not comparable to the observation for individually. These models are ocean atmospheric coupling models. And this black curve are the ensemble average of the individual models, and it's not simulate individual climate event or variability, but that's a long-term trend is somehow consistent, although the trend is a little bit larger, and the community still try to investigate the reasons for that, and it's caused possibly some forcing is not accurate in the models setup. This is a latest result to compare with the model simulation with stratospheric temperature observations, so the SSU channel 1, channel 2, channel 3, and MSU channel 4 is lower stratospheric temperatures. And the individual curves are from the chemistry climate model initiatives. It's not as much as the simplified models, about 10 or 15 models, but the spread is much smaller than the troposphere simulations, and the average, if you look at the details, the average trend from the simulations agree with the observation as very well. Sometimes it's identical. So this is a very encouraging result. One of the reasons of the smaller spread for the models is stratospheric dynamics. It's much simpler than the troposphere. It's only several processes need to be simulated well. This is an individual model simulation from NCAR WACCOM, whole atmospheric chemistry climate model simulations. Here is you have a SSD controlled run, and in that situation, all the simulation. This is include all the different channels. The red curve is the simulation, and the black curve is the observation. And the agreement is not only at the long-term trend, but individual variability and the climate event. So the model people say it's not surprising because the atmospheric models right now is pretty much good shape. It's the ocean model that's causing the problem with the simplified simulations. So that's a review of the status that we learned for the in the past, and the question now is, are we done now? It's of course not. We still have issues, and one issue is the satellite time series are different. So we show the anomaly time series of the mid-troposphere divided by the three groups that we mentioned earlier. You can see they're not agree that well. This is their difference time series, especially the difference between the remote sensing system and the UH are pretty large. It's sometimes about 0.2 Kelvin here, and the RAS and the star group agree well before 2005, but start to deviate from each other after that. And the groups try to work hard to understand what's causing the differences. But as a group, as a community, we hope that a different group can get the time series as close as possible. And because after all, the atmosphere has only one realization of the time series and the trend. And when you agree with each other, and also you need an uncertainty bar to define how it's close to the reality. And this is a global average. This is a tropical average, so the bias pattern is similar.
Because from us 2005, the red one goes down.
Yeah.
The red one goes up.
Yeah, that's a possibly reason quality control of the data set, and the downward drift treatment different, and the calibration drift treatment are different. All three different groups develop different algorithm to do the bias correction. And I'm going to talk about how we try to fix the problem. Also, if you compare satellite with
everybody's assimilating the same, all the AMSU channels, all the AMSU satellites at the same time?
Different group using different satellites, but they're all using the same channels, AMSU channel 2 and to AMSU-A channel 5. Combination could be different. And if you compare satellite with radio sound data, you find differences. This is a comparison between NOAA group, also temperature troposphere, with radio sound homogenized by different people. And this is a Harder Center data set. This is IOK, REACH, REPCOR, some of these are developed by University of Vienna. And you can say they're all different between the NOAA and the REACH and the REPCOR. The long-term trend are similar, except that there's sometimes it jumps. But the long-term trend are close. But with Harder Center, you see that drift starting from early 1990, and also REPCOR also have a similar drift. So we want to understand which one is more reliable when you find this kind of problem.
Excuse me, is this what's the height in the computer?
This is a mid-troposphere, AMSU channel 2. Yeah. And this is a co-located comparison. Consider apple to apple. It's not like satellite is a global mean. And because we match the satellite data with radio sound positions. And so hopefully to understand which one is more reliable, we need actually a micro reference observation or benchmark observation. And so we hope to have a micro sounder reference. It's not traceable to SR standard yet, but it's a kind of reference. It's a very stable. So this is a requirement for the reference. The requirement for weather and climate are very different, I think. For weather requirement, you probably need absolute accuracy better than the 0.1, 0.2 Kelvin, so that it can be similar to the NWP models without bias correction. Because if you don't believe this accurate, you have a bias correction before the simulation. But if it's truth, why you do the bias correction? I think that's why we come to this number. But unless the bias is absolute zero everywhere, the small bias but is unstable is no good for climate change detection. For example, if the bias is 0.1 Kelvin and you have a positive minus 0.1 Kelvin, and in a 10 years or 5-year period, it gives you a 0.2 Kelvin trend, artificial trend. It's no good for climate detection. So for climate, the stability is the #1 requirement. Constant bias can be canceled from the time derivative. And for the temperature measurement stability, George Irwin is in the paper in 2005 already give the specific number. It's a 0.04 Kelvin per decade for the tropospheric temperature and the 0.08 Kelvin per decade for the stratospheric temperature. So that's basically the 1/5 of the assumed trend in the atmosphere. Another requirement that we need a long-term observation and the continuity in channel frequency in the instrument design. But for the NOAA polar orbiting satellite, it's difficult to find this reference with good high stability before, because the satellite orbital drift. This shows the local equator crossing time of the from NOAA TARS N to NOAA 19, and also include the aqua. I need to sometimes disappear. These are aqua and ATMS now, and MetOp A and B. So before NOAA 19, all the satellites drift a lot, several hours. It's causing problems. I talk about in the next slide. But later the situation improved because the MetOp A and the MetOp B were launched to the same morning orbit. You can see the orange and the green curve. They match with each other very well in the stable orbit. And also in lower, the green curve, the aqua satellite, and the other one is SMPP. They're also close to each other. If you have the satellite orbit drift, you observe the different time when the satellite is aging, and that causing the bias drift. This shows the inter-satellite biases for all the for most satellite pairs when the satellites have a orbital drift. So you can see the bias is changing, and with a complicated pattern, it's drifting. Yeah. Okay. Yeah. So sometimes the drift is a kind of straight, and sometimes it's
This can be corrected. Basically, final variation.
Yeah. It's a lot of there's an algorithm to correct them, but it's not it's not perfect because it's every location and the time and in the globe the downward drift are different, so it's a challenge over there. And meanwhile, we have the calibration drift. The calibration is not perfect, and so this shows the one example of channel 6 between different satellite pairs compared to the different satellite compared with NOAA 15, and so it shows that the similar pattern for all the satellite pairs is suggesting that the NOAA 15 has a calibrated drift. This drift is have a long-term trend, also have a seasonal variability. That's not from the actual atmosphere; it's from the instrument. And so in many situations, this calibration drift and downward drift they mix together, and it's hard to evaluate the calibration drift when the satellites have a orbital drift.
Is this already applied for calibration, or this is before?
This is before with orbital drift. Yeah. But calibration is not because of orbital drift. It's the calibration part, but it's difficult to evaluate when you have orbital drift.
Right. After you apply, on the same line, is that overlapping?
Yeah. Right. So this is we come to the encouraging, I think exciting result when you have an orbit, when you have a stable orbit and two satellites at the same orbit. So this is the anomaly time series for the aqua, the blue curve, and it's from 2012 to now. And the red curve is SMPP ATMS, and this is their anomaly time series. So over there, overlapping period from end of 2011 and to now, they basically a perfect match with each other. And the green curve is the differences time series, and on the anomaly time temperature scales, like this from -1 to +1, you cannot see the difference, it's just 0. And so at the bottom panel, we amplify the time scale to look at the detail of these differences, and you can see that the difference, this is a global average The difference is within 0.02 Kelvin, and the standard deviation is 0.008 Kelvin. And the good part is the trend is 0.01 Kelvin per decade. It's well below the requirement that we talked about earlier. And these two observations are calibrated independently. It's not so that we recalibrate in at a time term and so manually doesn't match with each other. It's not the case. It's independent calibrated, and so its design is different. And the only explanation is that it suggests that both observations achieved absolute stability within 0.01 Kelvin per decade. And we not only examined one channel, we examined most channels that have a good quality, and this is different channels. Some channels the drift a little bit larger, but we can safely say it's already achieved the 0.04 Kelvin per decade for the stability. This is very good for the stratospheric channels, well below the 0.08 requirement, and also it also meets the requirement for the tropospheric channels. So what it means is that when you calculate the trend from this satellite, it basically tells you it's a real atmospheric temperature trend within the 0.04 Kelvin per decade. And when you have a accuracy like this high, and you can actually study some fine features in the trend. This is the asymmetric downward temperature trend. This is when you compare the morning satellite ATMS AMSU-A and afternoon satellite ATMS SMPP, and we found a little bit trend over here, and basically because orbital stable, it's just measure the a fixed time like 9:30, and another is afternoon. But basically, it's telling you that over the global land, over the in the lower troposphere, the midnight trend is warmer than the noontime trend by about 0.07 Kelvin per decade. I think this is the first time we observed this in the atmosphere, but it may be not new for the land, because years ago, people using the land observation found that the downward temperature range is defined as the differences between the maximum daily temperature and the minimum temperature. They have a trend about 0.06 Kelvin per decade, and this from satellite observation is very much consistent with surface observation now. That's a long-term trend. The asymmetry downward trend is only we only observe that over the lower tropospheric channels. But for the stratospheric channels, they still show the consistent near zero trend between different satellites, morning satellite, afternoon satellite, when the orbit is stable. So that's suggesting ATMS. No, MetOp also stable. It has some good aspect when we have this stable satellite observation. We can use it as a reference to validate or recalibrate other satellites. So this is we show an example. This is a collaboration between Hui-Hsu and Marian University. We're doing that now. Yeah, he's sitting there. So this is comparison between the MetOp-A and the MetOp-B. You remember that they are in identical orbit, both 9:30 orbit. So you are expecting if they're both stable you're expecting that give you a zero trend, zero time differences. But that's not, because in the 2016 October, there's a small jump. But this is a climate scale jump. But in the channel 5, its jump is only 0.02 Kelvin. And in the channel 4, the jump is 0.2 Kelvin. So it's not detectable in the weather scale sometimes. But and because AMSU-A is stable, so the only problem is MetOp B, AMSU-A. So we look at the, then we can look at what happened to MetOp B and examine the gain and other instrument feature. And we found the gain has a jump on October 2016 for every channel, and we asked what happened, and it indicated that at that particular day that turned off a channel 15. I don't know why that's causing the jump, but it's a manual that did something over there, and so we can use this reference to identify bias jumps, other satellites, and then find the reasons for that. And then we can develop the bias correction for that satellite. And this is pretty much simple, because we already have the references. We have a bias jump. We simply correct that bias so that the differences can be considered now. Okay. This is for calibration. And it can also help to improve the satellite quality, and this is a difference. This is a difference times between the AMSU-A and NOAA 15. NOAA 15 is very old satellite. It's 20 years now, and over the last few years, you can see from 2016 to 2018, the data quality and it developed a drift. The drift getting larger, and it's causing the uncertainty and the trend inaccuracy when you include this satellite. But with references, we can improve it. The blue curve is the before recalibration, and the black curve is after recalibration. So you can see it's compared to the references, the quality is much improved.
Why is not like a print?
Huh? Yeah. The reason is the nonlinearity, calibration nonlinearity is changing with time. So after 40 years, we recalibrated once 10 years ago, but then after another 10 years, it's not good to calibrate the original NOAA 15 anymore. So with the NOAA, the black curve is we developed a new calibration coefficient, and then it should match better with the reference satellite. This particular channel, channel 5, the downward drift has a big impact on the over the land. It is large. Over the ocean, it's small. So if there's a difference, we think it's caused by calibration error. It's not the downward. If you do land over land, then you cannot use the methodology because it's a downward problem. Right? You have to separate them.
And did you have similar plots for the other AMSU satellites?
We're still doing that. Yeah. This is a preliminary result, but we are doing all the satellites now to evaluate their stability. Yeah. And so this is some perspective. We're still working on that. We hope that this stable satellite observation can improve the CDR. We use that as a reference because we know it's stable, and we merge all other satellites one by one, try to hopefully the bias drift can be very well removed, and the uncertainty very controlled. And also use this to develop better dynamic correction algorithms. And it may have other impact on the other instruments observation. For example, we compare the radio sound with satellite. We found the differences. So with the stable satellite observation, I think we have a very good case now. And now, if you compare radio sound with aqua and ATMS, and if you found the differences, different drift, we have a better case or better confidence say, oh, that's probably the radio sound problem. And then you can look at the try to look at the reasons for the drift and improve the radio sound observation. And also, people compare the GPS RO data with the aqua observation, and for the stratospheric channels, the agreement is within 0.04 Kelvin per decade. This is consistent with what we found in here today. It's very good. And finally, it probably have a impact on climate reanalysis. For that, I show a few plots. This is a bias question for the reanalysis. When people do data simulation, satellite data simulation in the reanalysis system, they do bias question to the satellite before simulation, and this is the time series from the ERA interim, and so we can see that here. If you see the aqua, this is a channel 9, and it's suggesting okay, the satellite bias has a long-term drift based on the bias correction, but we just showed that it's not the case. The aqua and the ATM is quite stable, and so this may suggest that the model drift. Have a better suggestion on that now. So this is just a suggestion that it be in the model climate reanalysis when you do the bias correction, we consider the stability of the satellite observation. Even for the other satellite, we never observed that large drift. So that's a.
For the channel 9, you see for coverage from 2005 to 2008, you say with model drift, but if you think this is after the calibration, the reanalysis after the calibration, let me compare with the model reanalysis. Am I right?
No. This is no. With for the aqua, we basically did not do recalibration. The recalibration is just we add a different offset. We did not change the nonlinear coefficient. So the aqua observation here is basically the same as we use for the evaluating when compared with ATMS, the same kind of data set. That's a.
Yeah, maybe we can talk later. But how to believe the model have a 0.8 Kelvin drift of wire within those years? And I do not understand.
I don't either. But when you compare the reanalysis trend with the satellite observation, it's not that much different. I don't know how come eventually reanalysis, the final, but this is a bias question is a difference between the satellite and the model forecast. It's not the final reanalysis. So, but the model forecast, it looks like it has a long-term drift, and it's corrected more and more by the observation, and we need to. But that's Craig maybe have more saying on that, but it needs reinvestigation. That's all I say. Okay, now we got a summary. And the global mid-troposphere temperature warmed 0.7 Celsius degree during the last 40 years, and tropospheric temperature trend over the northern polar region is much larger than the global mean, and upper stratospheric cooled 3 Celsius degree globally during the last 40 years, and global climate modeling has made significant progress in simulating the past climate change, and ocean modeling may need some improvement. And I know the CME 6 model simulation result already released, and we're looking forward to that to comparison between that project and the satellite observation. And then the SPP ATMS and Aqua MetOp-A and AMSU-A observation achieved the stability performance of 0.04 Kelvin per decade. That's a major new things that we have today, and also we expect the high radiometric stability performance to improve the measurement of atmospheric temperature trend. And yeah, thank you very much.
So questions?
In the beginning, actually, you showed that there are 3 trends. You know, one, Christie's results showing like this, and yours showing like this. Okay. Then you talk about recalibration stability. Did you go back to check that diagram showing totally opposite trend of your product and Christie's product for that one? That's very crucial. It seems here you have fixed your satellite problem. Yeah, this one, the lower left one.
Yeah.
So what's the implication based on your later work to explain this diagram?
I don't have the latest version of STAR data yet. We are developing version 5. This is based on the version 4 and the version 3. And we are doing that, and hopefully we develop better product in the next 1 or 2 years. And then we can reinvestigate these differences and have a better uncertainty.
This is RSS minus UAS.
Yeah.
You should using RSS minus star, then UAS minus.
Yeah, but basically you can the RSS minus star is here. It's pretty much agree, and the difference. I mean, we can add another term, but basically it's just tell you the differences between different people.
I think my concern is you see this kind of and then people using three sentence results, then take together, and then say the mean, and then like Ben Sanders published that paper, right? The previous one published the paper saying that everyone saying that the increasing particle years.
Yeah.
But that's
I agree, but before we know, or it's a democracy. Yeah. I hope to include it. But by this, you have more groups. You can characterize uncertainty bars by intercompare with each other. But that's not the best approach. But now I think with more stable satellites, we probably can improve that situation. Yeah.
Cheng-Zi, that's very nice. You have shown the global mean, the values of the global mean, and then use that global mean as the indicator of you achieving the threshold of climate measurement. The threshold that you mentioned is like 0.04 some Kelvin, or those numbers that you mentioned. So my question is that have you checked, like instead of global means, on hotspot areas where climate change has actually impacted, and whether you are able to extract signals of certain areas around the globe which have been impacted by climate change?
I didn't quite catch your question.
I mean, you use the global mean actually.
Yeah.
So that is the global mean actually. But can you, from your times, from your record, also identify geophysical locations around the globe that have been impacted by climate change?
Well, yeah, it did. Some.
No, but
yeah,
your measurement can
zonal means and have been compared in some papers, and the seasonal variability have been compared between observation and the model simulation. It's a lot of studies on that. I just don't have much slide to show all these different results. Yeah.
Okay, so with that.
Very quick question. So this different trend, you just don't have any way to constrain them. In other words, you have no absolute reference to see which one the trend is more likely to be right or wrong. But physically, as you said, the Earth only has one realization. We know that should be one is true, one is not true. And why don't you use the solar radiation? We know the planet Earth must maintain balance. So the shortwave radiation does not change with the time because planet albedo does not change. So if you can do a back envelope calculation to calculate the brightness temperature of the Earth and to see which one is consistent with the broadband brightness temperature. That will be one way to check which one is right or wrong. Just based on the very basic Earth energy balance, the outgoing and shortwave, they must be balanced. And that way you can go check the trend, see if they are consistent with this total brightness temperature.
Yeah, we can. We can do that maybe some other time to see which one is.
Yeah, we're talking about temperature, but temperature, we're talking about different altitude temperature. When you integrate them, you do radiation transfer, you get the entire planet temperature. Right? So see which one agree with the real brightness temperature of the entire Earth. In that case, you have to do the full global mean.
But I don't know if that that comparison can detect such a small differences between different groups. The error, but we show these differences, but we actually have within the groups. We understand some groups may make mistakes when do the algorithm corrections, and or it's not physically it's not very sounding in the algorithm. Also, lack of document. We know that some groups, it's in historically, I don't want to say very, but historically they made some errors in the correction. Yeah.
But we got an online question. So it's asking, can you tell us some of the fundamental methods about how to calibrate satellite time series among different multiple satellites to align them together with observed climate record? So
can you repeat again?
So he's asking what's the fundamental methods that you are using to do the intercalibration?
Read
the paper. Okay, got it.
Yeah, we use an integrated microwave calibration approach. Yeah, we assume that the calibration error is caused by calibration nonlinearity, and and we try to use simultaneous energy overpasses and global ocean mean differences, and try to characterize the biases between different satellites, and then modify the calibration coefficient so that you can the different satellites can match each other better.
Okay, thank you.
Great talk, Cheng-Zi.
Thank you.
Yeah, a couple things. One is the altitude drop correction. I know Frank Wentz made a big splash in about 1999, 1998, 1999, 2000, regarding the change in temperature due to the altitude of the satellite itself, especially with the scans, the outer scans, and also how do you handle the NOAA 9? I think it was NOAA 9, NOAA 10 3-month overlap, because the overlap is critical really to intercalibrate. And how did you deal with that one? 2 questions. Sorry.
Yeah, that's a good question. You know, when we match them together, we use all the overlaps, even shorter, sometimes longer, and solve this multi-regression equation simultaneously. And so whatever results we get over there, and we accept it, and after that we examine the biases for that 3-month period, and then we compare some other group like a Cheng-Zi group to compare that the merged time series that instrument temperature effect was removed, and then compare that with radio sound data observation, and get a feeling, okay, all the temperature effect was very, very removed because of correlation between radio sound and satellite observation are much more reduced. That gives us some confidence, even though it's just only 3-month period, but we can do a little bit more of validation work for that. But again, it's not 3 months is short. Yeah, I agree.
And the altitude drop, did you incorporate that into your analysis?
Huh?
The altitude drop of the satellite.
Yeah, and also it's you know, it's before, you notice before, this series before 2005, the RAS and the NOAA group agree with each other very well. That includes the time period that you mentioned. That we solved that equation independently, and that gave us some confidence.
Great, thank you.
Okay, so with that we conclude the speech, and let's thank the speaker again.
Very interesting talk. What I said is actually doable. 你们这个首先是你今天主要讲 ocean， 在 land 上面是不是同样的 product 没有？在 land 上面这个产品用没用在这里边
？land 上的 difference 更大一些，因为 land 上的 Donald effect very large。
对。
land 上面呢，因为你要